Assalamualaikum and welcome. Today we're gonna talk about a digital dice. So, what is a digital dice? Digital dice is an electronic simulation of a traditional six-sided dice designed using digital logic circuit. Instead of physical rolling, the dice operated using a clock pulse to generate random like number between 1 and 6. The circuit is built using JK flip-flop to create a binary counter which cycle through the dice value. A 7447 BCD to 7-segment decoder is used to convert the binary output into a readable numeric number. When triggered, the circuit generates a new dice value based on the clock signal, ensuring fair and unpredictable result. The project demonstrates key digital electronics principles, including sequential logic, counter circuit, display interfacing, and synchronous clocking mechanism. It is a practical application of logic gates, flip-flops, and combination circuit, making it useful learning experience in digital system design. Purpose of this project. First, to simulate a dice electronically using digital circuit. Second, to apply JK flip-flop, counters, and logic gates in a real project. Third, to understand how sequential circuit and 7-segment display work. 4. To learn how to convert binary number to decimal using a 7447 decoder. 5. To improve circuit design and problem-solving skill. Objective of this digital dice project. First is to design a digital dice that generate number from 1 to 6. Second is to build a binary counter using JK flip-flop. Third is to interface the counter with a with a 7447 BCD to 7-segment decoder. Four, to display the output clearly on a 7-segment display. Five, to apply an understanding digital logics and sequential circuit concept. So, how it's work? First, clock pulse generate a clock signal act as the trigger for the digital dice. Each pulse from the clock increment the dice count. Second is binary counter using JK flip-flop. The JK flip-flop form a 6-mode counter from 000 to 101 in the binary, ensuring the dice only display number 1 to 6. The counter resets after reach 6 to maintain the correct range. Third is binary to BCD conversion. The counter output a 3-bit binary number representing dice value. This binary value is sent to a 7447 BCD to 7-segment decoder. Fourth, display output using 7-segment display. The 7447 decoder converts the binary output into signal for the 7-segment display, ensuring the correct number 1 until 6 is shown. Rolling mechanism. The fifth is rolling mechanism. A button press or external signal activated the clocks, making the counter cycle rapidly. Releasing the button stop the clock, freezing the display at a random number between 1 and 6. And here is the state table. As you can see, the present state from Q2 to Q0, 001, and then the next state is 010, and then that 010 back to the present state, and then the next state is 011, and that 011 from the next state will go back to the present state, and then the next state after that is 100, and it will continue until it's reached back 001. Uh, this is in a binary number, and at the right you can see the can see the excitation table. From the state table and the excitation table, we can produce the K map, and here is the K map for the circuit. From the circuit, we can get a result to make to this to construct the circuit. But in this circuit, you can see that I'm not using the seven segment BCD counter. But in this circuit, you can see that I'm not using the 7447 BCD to 7 segment decoder because I get a little bit problem around here. So, but because of that, I put this pin assignment using the 7447 pins. So I think when we put this on the DE2 board, it still work even though without the 7447 BCD to 7 segment counter. It's the same, but I have to do it manually. I got the problem to the circuit to convert here. But the way this circuit works is already been told earlier and how it's worked like. So this is how the result will look like. This is the circuit. So the discussion will be digital die successfully use JK flip-flop to count from 1 to 6 in binary. A reset logic is implemented to prevent the counter from going beyond 6. And then the 7447 decoder convert the 3-bit binary output into a readable number on the 7 segment display. The circuit demonstrate how sequential logic can be used for real-life application like gaming. One challenging phase was connecting the 3-bit output to a 4-bit output of the 4774. This was solved by grounding the unused input. The project helped in understanding clocking, counters, and display system to a practical implement. In conclusion, the Digital Dash project successfully demonstrate the application of digital logic in simulation in a real-world object. By using JK flip-flop, logic gates, and a 7 segment display on the DT board, the circuit is able to generate number from 1 to 6, just like a traditional dice. This project not only reinforced theoretical knowledge of counter, sequence circuits, and binary to decimal conversion, but also provide hands-on experience in designing and implementing practical digital system. Overall, it serves as a valuable learning tools and a stepping stone for more advanced electronic application in the future. And that's all from from my team. Thank you.